Good afternoon, everyone. I think we're going to get things started. So, first of all, I'd like to welcome you all to this Galileo lecture event, put on in partnership with Royal Astronomical Society of Canada and also the Canadian Astronomical Society. So, just to start you off, well, you notice these pictures being passed in the background here. These are all photographs taken by members of the Ottawa Centre for the Royal Astronomical Society of Canada. And in case you're wondering who I am, my name is Paul Harrison. I'm the president of the Ottawa Centre for RASC, and I'm delighted to be your host for this afternoon. So I'm just going to set up another set of slides here, so just bear with me a moment. Okay, so as you can see, our main speaker for today is Dr. Roberto from the University of Toronto, and he's going to be talking about cosmic dawn and monster telescopes and understanding some of the origins of our universe. So who's the Royal Astronomical Society of Canada? The RASC is a national organization of 29 centres coast to coast dedicated to astronomy, to basically promoting astronomy, to promoting interest in astronomy. Most of our members are amateur astronomers, they're people from all walks of life, but with a common interest in understanding more about the night sky and the various mysteries behind it. And we also are very interested in promoting astronomy and our hobbies, so we're always happy to interact with the public and gain further interest. So, just a little bit about the RASC Ottawa Centre. So again, we're one of the 29 centres of the RASC. For those who are interested in finding out more about astronomy, getting involved, being interested in some of these activities that we do, our centre has monthly meetings. We meet at the Canada Science and Technology Museum, St. Laurent Boulevard. Our meetings are held first Friday of every month at 8:00 p.m. We have a lot of fantastic presentations there. Just members there showing images or just showing the general interest in astronomy topics. General public is always welcome, and there's no admission fee and no restriction on who comes. We're always happy to have you come out and learn a little bit more and get to know some of the other people who share your interest in astronomy. For those who want to find out a bit more, I've got our website and email address up there, so please feel free to give us a shout if you'd like to find out more and to get involved. So you've probably been seeing this logo around a fair bit this year. As many of you know, this is the International Year of Astronomy. The reason why 2009 has been picked as the International Year of Astronomy is that in 1609, 400 years ago, a gentleman by the name of Galileo Galilei pointed his telescope up at some of the planets and stars and started to realize that our universe is a slightly bigger place and has a few more things in it than previously thought. And of course, now 400 years later, we have a lot of incredible telescopes and other instruments that are showing us the universe is a much bigger, fuller place than Galileo himself could ever have imagined. And we're very delighted that we have someone here involved in a lot of that work to talk to us today. So just to give you an overview of what we're going to be doing this afternoon. So we mentioned our central piece is the Galileo lecture with Dr. Roberto. This will be followed by a question and answer session. We told Dr. Abraham loves questions and be happy to take yours after the talk. After the presentation, RASC Ottawa Centre's Rob Alexander and Penelope Goranson will be giving us a musical interlude to an astronomy themed song to guide us towards our afternoon. So, after the lecture and musical show, we are obviously happy to notice displays out in the corridor put on by the members of the Ottawa Centre RASC. So you can learn a little bit about a number of different aspects of astronomy. We have meteorites and meteorite craters, so we can find out that you can study space without necessarily always having to look up. We have telescopes of all shapes and sizes, although not as big as the ones that Dr. Abraham is going to be talking to us about. Quite impressive nonetheless. Sorry, a little bit further. Light pollution is obviously a big concern for those of us who are interested in looking at the night sky but tend to live in cities. And so we have a display on there talking about the challenges of light pollution and trying to keep it to a minimum. And finally, we've been very fortunate. Mother Nature has cooperated in giving us a sunny day, so we'll be able to see the sun. And we've got a few telescopes set up for safe solar observing. And again, you can see that not all of astronomy requires staying up into the wee hours of the night. And we may even be lucky enough to see a planet or two even in the daytime. So, to introduce our guest speaker, I've got a few notes here on him. So, Dr. Roberto Abraham is a professor of astronomy and astrophysics at the University of Toronto. He's also principal investigator of the Gemini Deep Survey, an international project designed to study galaxies formed when the universe was only a few billion years old. Very, very young. Dr. Abraham and I share something in common. We both got our bachelor's degrees at UBC. His was in astronomy, mine was in engineering. Dr. Abraham got his doctorate at Oxford, which I didn't. Afterwards, Dr. Abraham did his postdoctoral work at several institutes, Dominion Astrophysical Observatory, Institute of Astronomy in Cambridge, so you managed to do both Oxford and Cambridge, and the Royal Greenwich Observatory. As part of his research, he developed and automated classification systems for the shapes of galaxies. The system was actually used and has been applied to data from the Hubble Space Telescope, which we've been seeing a little bit on the news about. We're fortunate to have that around with us for at least a couple more years. Dr. Abraham's many awards include the Stacey Fellowship, the National Sciences and Engineering Research Council of Canada, the Canada Foundation for Innovation Career Award, and the University of Toronto's Outstanding Teaching Award. And just as a final mention, Dr. Abraham also happens to be the honorary president of the Toronto Centre RASC. So one other thing, again, just to point out, is that we owe special thanks again to the Canadian Astronomical Society, known as CASCA, for their incredible support for this event. So without further ado, I would like to hand the floor over to Dr. Abraham, and we'll find out a bit more about the mystery of the universe. Go.
All right, well, it's a pleasure to be here. How's the sound? That sound okay back there? Great. Okay, so I'm going to be talking today about a number of things that I actually work on that I hope you guys will find exciting, because you are fortunate to be alive, I think, at a miraculous time in the history of civilization, when we are finding out for the first time an incredible number of things about the nature of the universe. It's somewhat akin, I think, to being alive in 1492, when America has just gotten discovered. We are just discovering the most fundamental things about the universe, and it's happening at a time when you happen to be alive. Now, let's start at the beginning, okay? So we will start with the act of creation. We will start with the moment at which the universe was formed from nothingness. We now know that this happened 13.7 billion years ago, plus or minus a little bit. That's an example of what I mean about, you're lucky to be alive now. When I was in graduate school, we didn't know the age of the universe to within a factor of 2. It could be 8 billion years old, it could be, 30 billion years old. We just didn't know. And now we know exactly what it is. Now, you would think then that though the universe being this big mysterious thing, and it is, that we don't know very much about the process of creation itself. And you would be wrong. It turns out that the process by which the universe emerged from energy at the time of the Big Bang is actually something that's really well understood. And in order to explain it to you, I'm going to do something that people tell me not to do when giving a public talk, okay? I'm going to show you an equation. But don't be scared, okay? This is the only equation. And Furthermore, I can get away with this because this is an equation that you see on t-shirts and stuff, right? Everybody knows what this means. And if you don't, I'm going to tell you now, all right? What it means is that, does this sound okay? It sounds a bit weird to me. Are you sure? I don't want to drive you crazy with it. Okay. Well, okay, let's see if we can get this laser pointer going. That would be no. Okay, I'm going to do it with my fingers, all right? What this equation is telling me is that energy and mass are aspects of the same thing, all right? It's telling me that I can take a bunch of mass and I can turn it into energy, and I can take a bunch of energy and I can turn it into mass. And the reason we are sure that this equation is one that we can rely on is a sad one, okay? And here's the sad reason. We know how to blow stuff up using this equation. Do it all the time, okay? So as a result, usually when you look at this equation, you think of it as a destructive thing. What you're doing is you're taking a few kilograms of uranium or plutonium, turning it into a bunch of energy and a lot of destruction. Okay, so that's bad. So when you look at that E equals mc squared and you think of a nuclear bomb, you should be kind of depressed. But if you feel depressed when you look at that equation, it's because you don't understand it. Okay? And somebody who did understand it and who's often misquoted is J. Robert Oppenheimer, the father of the atomic bomb, who is often misquoted as having said, upon witnessing the explosion, the Trinity explosion outside of Alamogordo, New Mexico, the first atomic bomb, he's misquoted as having said, "I have become death, destroyer of worlds." But he didn't say that. Never said it. Okay? What he actually said was, "Now I am become Shiva, destroyer of worlds." Oh, sure. Okay. Hold on, you're going to be driven crazy for the next few seconds. How's that? Better? Okay. Let's try that. Okay. How's that? Better? I'm moving my head. All right. So what Oppenheimer meant by this, okay, what Oppenheimer meant was that, and he was a student of classical Hinduism. What he meant, okay, was that the god Shiva in the Indian pantheon is a god that is associated with both creation and destruction. What you see up there is Shiva doing this thing called the Nataraj dance. So Shiva hearkens the destruction of the universe, brings it in, and then when the universe is destroyed and left as ashes, Shiva does a dance which brings forth a new universe. So what Oppenheimer meant was that the destructive force is also a creative force, okay? So both aspects of that equation were known to him, and they're crucial for understanding the creation of the universe. So we mimic the process of the Big Bang all the time. That's the whole reason for building particle accelerators. So this is a detector, part of the Large Hadron Collider. This is being constructed just outside of Geneva in Switzerland. The whole point of people who build things like this is to try and have something akin to a miniature Big Bang. So this is data from a similar type of experiment, and what you see when you look at this is creation, okay? I'm gonna try and point with my finger here. If you see a little particle emerging from nothing and then splitting up into other things, what you're seeing there is things emerging from pure energy, making matter from pure energy. Very, very similar, identical to what happened at the time of the Big Bang. So the processes by which our universe emerged from the Big Bang are known. You can do it in a lab. We do it all the time. We do it millions of times a day in these labs. So what's the problem? Do we now know the creation of the universe to some fantastically accurate level? No, because the problem is the universe that emerges from this process is dull. It's boring. The processes that I've just described will make this. Okay, so on the left we have hydrogen, on the right we have helium. The processes that I have just described will make hydrogen and helium. That's it, okay? The universe of hydrogen and helium is a boring universe. That's nothing like our universe. Really what we want to know is how to go from the boring universe of hydrogen and helium to the fantastically rich and diverse universe full of all the good things, which for purposes of this talk, I'm going to caricature as biodiversity, sex, sunsets, chocolates, and booze. Okay? How do we go from this to this? It turns out that the answer is also known. And the answer is you use a star. Okay? So stars are the furnaces of creation. Stars are mostly hydrogen and helium, but the processes through which stars shine create the chemical elements in the universe. The carbon that's in me, the iron that's holding this thing up, all were formed in a star, either as the process through which it shines or as a process through which it dies. Okay? So metals tend to be formed in supernova explosions. So stars are a catalyst for complexity. The universe that we see around us is largely the product of taking the raw material of the Big Bang and processing it through stars, and what emerges is complexity. So, sounds like we understand what's going on. Well, no, because now we begin to hit a mystery. Okay? And the mystery is that there are two fundamental problems with the picture that I've just described. So here's the first problem. We don't know how to make stars without stars. What does that mean? Okay? So we know where stars form. Stars form in these clouds of gas and dust. So these things are called nebulae. So this nebula shown here, this nebula shown here is the site of the birth of stars. But what is that nebula made out of? Well, it's made out of things like carbon, okay, which is the most important constituent of dust. But where does that dust come from? That dust comes from stars. So if you need the processes of previous generations of stars in order to make stars, how can you possibly have the first generation of stars? How do you make the first stars? We don't know. Okay, so that's mystery number one. So what do you do if you're a scientist and you run up against something that is deeply mysterious? I'll tell you what you do. You give it a name, all right? Because you give it a name and then you feel better. Even if you don't understand it, you give it a name and you feel better. All right, so we give this a name too. Okay, we call these stars, the first generation of stars, population 3 stars. So we see population 1 stars, we see population 2 stars. Nobody's ever seen a population 3 star. We know nothing about them, but we give them a name and we feel better. All right, so that's the first problem. Okay, is we don't know how to make stars without stars. Second problem is we don't know how to make galaxies either. So it turns out that if you make a star without a galaxy in which it lives, it's not going to participate in this cycle of making the chemical elements. So manufacturing the chemical elements, the complexity of the periodic table, the rich, complicated universe you see around you requires cycles of birth, death, and rebirth, making many generations of stars. And the products of these many generations of stars gets launched out into the universe. But if those stars don't live in a galaxy, that stuff just gets launched out and it never participates in making new stars. What you need is a ton of other stars collected together so that stuff agglomerates and makes more stars. So you need galaxies, huge collections of stars. You can't make these stars in isolation. Now, the problem is we don't know how to take the stuff in those bottles, the pure hydrogen and helium, and make a galaxy out of them. Okay, it won't work. It collapses on all the wrong sizes and in all the wrong timescales to make galaxies. So, it turns out that we know the cure to this problem, okay? And the cure to this problem is to take the stuff in those bottles and do something to it. And what you do to it is basically something that will surprise you because you've been lied to. All right, so here's the big lie. And I know this is a big lie because basically I've got kids now who come home from school and say stuff like, "Daddy, we learned in school today that everything in the universe is a solid or a liquid or a gas." And I say to my sons, no, 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 no. Okay, even though I was told exactly the same thing. All right? So you know who got it right? These guys got it right, the ancient Greeks. These guys, I don't know how they did it. Those clever, wily Greeks, okay? Thousands of years ago knew the truth, all right? And the truth is that there are more than 3 phases of matter. So they told us that everything in the universe is earth, air, fire, and water, right? So earth is a solid, air is a gas, water is a liquid. What's fire? Right? So fire is this thing called a plasma. Okay, so a plasma is another phase of matter. Right. So I'm going to explain to you what a plasma is using an analogy that I thought up myself. All right? But you are free to take this now and use it for whatever purposes you want. It's a brilliant analogy, I think. You tell me what you think. All right? So here's, and it's, what's brilliant about it is its audience participation. So I want you to participate in this. All right? So I'm going to make you guys into a big solid. So go to your neighbor, okay, and hold their hand. Hold it tight now. Tight. Grasp their hand. Come on, Al. Hold her hand. Okay, now hold it rigidly. Okay? Now what you are a bunch of atoms. Okay, you are atoms, and you are locked tightly, rigidly together. Okay, you are now a solid. Okay, now what I want you to do, okay, is in kind of an effete way, don't lock together so rigidly, but sort of hold, your pinkies, Now what you are is a liquid, all right? You're bound together, but you're not locked together very tightly. Okay, so for the next one, there's going to be no audience participation. Okay. For you to become a gas, what you have to do is stand up and run around randomly, smashing into each other, okay? Running around faster, and the faster you're running, the hotter the temperature of the gas. Okay, that's a gas. Now, this is the one where really there's no audience participation. If you want to be a plasma, what you do is you stand up, take off all your clothes, and the clothes just run around randomly bumping into each other, and then the rest of you, naked you, runs around and bumps into other people who are also naked. Okay? I think it's a brilliant analogy. All right, so
sounds like a good party.
That's a good party too. A good party trick. Okay, so that's what a plasma is. Okay, what a plasma is it's like a gas, except what's happened is that the outer part of the atom, okay, the electrons, the outer garment of the atom, has stripped off from the rest of the atom and is behaving independently. All right, so that's what a plasma is, and that's what you got to do. So how do you make a plasma? Well, you hit a gas with a lot of energy. All right. And if you have a plasma of hydrogen and helium, then it turns out that plasma of hydrogen and helium will collapse on the right scales and on the right times to make a galaxy. Okay, so it turns out then that that's an important process in the universe. Somehow you have to take the stuff created in the Big Bang, that's like in those bottles, and hit it with a bunch of energy. And if you do that, you will wind up with a complicated universe. So sometime after the Big Bang, okay, all of the universe created got blasted with energy. All right, so I lied earlier when I said there was only one equation in this talk. It turns out there are 2. Okay, this is the second one. So this equation is the Big Bang makes the stuff in this bottle. Something happens, and you wind up with a universe that is a plasma. Okay, so what do you do when you run up against something you don't understand?
Give it a name.
Give it a name. So that's what we've done, because we don't understand the first thing about this process, but we've given it a name. This name is called first light. So first light refers to something that happened sometime after the Big Bang that blasted the universe full of energy and that set us on the road to the complicated universe that we live in today. If first light never happened, there would be no stars, there would be no complicated structure, there would be no people. Okay, so this first light is basically the origin of complexity in the universe. And we don't know anything about it, but we give it a name, and that makes us feel better. So, first light has in essence, become the holy grail of observational cosmology. This is now pretty much acknowledged by most people working in this field as the thing we've got to understand, the thing that is worth spending billions of dollars on, focusing our energies upon in order to make the next big breakthrough in understanding the nature of the universe. It is the holy grail of cosmology today. So what does that mean? It means that astronomers are on a grail quest. Okay, that's what we are. When you see me, you should imagine me being this guy. Okay? And you should imagine Al Scott, who's right there, member of the Ottawa RASC, as being that guy, because Al is inextricably linked with everything I talk about from now on. All right, so let's recap. So, something happened to the universe after the Big Bang. Big Bang occurred 13.7 billion years ago. Something happened subsequently that blasted the universe with energy. That energetic phenomenon turned all of the hydrogen and helium gas, the stuff in that bottle, turned it into a plasma. That plasma collapses on the scales required in order to have a complicated universe. It creates galaxies. You need galaxies to have the complicated universe. We don't understand this process, so we gave it a name, and the name is first light, okay? Finding first light is the mission, all right? People who have Nobel Prizes or who want to have Nobel Prizes are all focusing their energy upon this thing, because that's the thing we want to do. So, prior to first light, we also give things a name, okay? Remember, don't understand something, give it a name. So, prior to first light, we live in a universe completely different from our present universe, right? No stars, no complexity. How does, how do the first things that ultimately led to first light emerge from this boring universe? Nobody knows. So we give it another name, okay? We call it the cosmic dark age. So the idea is the Big Bang occurs, the universe is left in a state that we refer to as the cosmic dark age. It evolves for a while, and some process leads to this huge injection of energy into the universe. We call that process first light. Fast forward 13 billion years, and what you wind up with is the universe we see around us today. Now, we don't know a lot about this process. We've really hit the wall of our knowledge. We're now pushing forward the frontiers of astronomy. We're really faced with our ignorance here. That's a good thing, okay? That basically is where you want to be, because that means you're probing the most exciting stuff. And that's where we are. And it turns out, and this is another example of how exciting it is to be alive today, it turns out that even just in the last few years, we've learned a fair bit about first light. So it turns out that there are now things that we know about this process. A few years ago, it was, we're completely clueless. All we can do is give it a name. Now we're less clueless. We don't know what caused first light, but we at least know, for example, when it occurred. And that's huge progress. So, we don't know what it is, okay? We don't know what caused it. We think we can eliminate a few things, okay? So, for example, one possibility you might envision is that the Big Bang created a lot of black holes. Those black holes suck matter in, and that sucking in liberates a bunch of energy, and that's first light. Turns out we can probably eliminate that, okay? Because those, the matter streaming into those black holes, we give those a name too. We call them quasars, okay? So it's probably not quasars. It turns out that if it were quasars, the reionization would be very patchy, and we've established that that's not the case. We also know it's probably not a known population of galaxies. Whatever caused first light has to look completely different from familiar things, and I'll show you why in a moment. Bottom line, okay, is that we now know it's probably going to be something weird. Now, that's kind of good. It means that there's, opportunities to learn new things. Another good thing is we at least know when and where to start looking, okay? Because we now know that first light probably occurred about 200 to 300 million years after the Big Bang. So the universe is presently 13.7 billion years ago, billion years old. First light occurred in the first 200 to 300 million years after the Big Bang. So at least we know roughly where in cosmic time to search for first light. And that is also huge progress. What we don't know, though, is whether or not it occurred quickly or whether or not it occurred over an extended period of time. So let me tell you why we know some of these things. This is an example of a spectrum. So this shows the amount of light coming out as a function of wavelength or color for a couple of very distant objects. I don't want to, if I turn around, it's going to sound funny. Does that sound okay? Okay, so if you look at the object at the top there, you can see a bunch of bumps and wiggles. Some of those bumps and wiggles correspond to chemical elements other than hydrogen and helium. So you know when looking at that object that it is not made of whatever made first light, okay? It's got oxygen, it's got silicon. So that thing, even though it's very, very far away, cannot be an example of one of the first things in the universe. Stars have existed prior to that thing. So you can work out how far away that thing is, how old it is, and then you can just using basic logic conclude that first light must have occurred before this thing. So using those sorts of arguments, you can work out when it occurred. So another thing you can do is you can count the number of galaxies that you see in the universe as a function of distance, and work out whether or not the most distant objects that you see are pumping out enough energy in order to have participated in this process of first light. And the answer is no. Okay, so this is currently the world record holder most distant galaxy known in the universe. And we can count how many such similar things are out there, and the answer is they're pretty rare. Okay, so there are not enough very distant objects for those things to hold these so-called population 3 stars, and as a result, be participants in this first light thing. Okay, so, sure. Can I give you this? Okay. Just carry it out. Carry with you? Sure. Let me get rid of this thing then. Okay. Okay, no problem. There you go. Thanks. How's that? Okay, we're going to do the Elvis thing. Thank you very much. All right. Okay, so what might it be then? Okay, those last 2 slides were just to basically illustrate, the basics of what we think it can't be. What might it be, and how are we going to find out? So there are basically 3 ways you could envision finding out the sources of first light, the origins of complexity, and this being Ottawa, they all involve money. All right, so I'm going to do this from the point of view of how much money these things are going to cost. So option number 1 is first light might be made up of weird stars blowing up. If so, it's going to cost you, the taxpayer, or the world's taxpayers, mostly the US taxpayer actually, $300 million. So if first light is made up of collections of weird stars or black holes, it's going to cost about $6 billion. And actually, you're on the hook for part of this, if you're Canadian. Okay. If it's made up of collections of weird stars, but in a very limited period of time in the universe, then it's only going to cost you $20 million. What a deal. And you as the Canadian taxpayer only pay a tiny fraction of this. Now, more to the point though, if it's made up of weird stars blowing up, then you would find out about it right away because of a mission that's up there now. If it's made up of collections of weird stars and black holes, it's going to require a mission that's going to be launched in a few years, which I'm going to talk about in a moment, and we would find out about it in 2015. And if it's made up of weird collections of stars and black holes, but in a limited period of time, you may find about it next year, and I may be the guy who finds out about it, in which case you'll have heard about it first from me. Okay, so now here's the exciting thing, okay, and this is progress in science. I am now able, pretty much for the first time, to do this. Okay, no. First light is not made up of weird stars, so-called population 3 stars blowing up. This is something I couldn't have hit the space bar and made that line appear a year ago. Okay, so this is something we've learned, that by looking for these things using this satellite, we have shown that there are not enough things blowing up in the distant universe to be responsible for first light. So really what we need to do then is just consider the next 2 options. Okay, so the second option is the most exciting option. And that is to use the successor to the Hubble Space Telescope, which is a spacecraft known as the James Webb Space Telescope, and it is designed from the ground up to look for first light. Its entire reason for being built the way it is being built is to look for the origin of complexity in the form of this first light. So here's a mock-up of this thing outside of the company that is manufacturing most of it. And here is a movie showing the plan. So I'll let the movie run and then explain it. So unlike the Hubble Space Telescope, this thing is not going to be in orbit near the Earth. Instead of it's going to be at something called the Lagrange 2 point, and it's going to be out beyond the moon. It's too big to go up in a rocket fully assembled, so it self-assembles as you get further out. So, I wonder why that's playing. Anyway, how exciting. All right, so this Hubble Space Telescope successor, the James Webb Space Telescope, is going to go out beyond the moon, and it's going to unfold like an accordion. And its mirror is going to be 6.5 meters in diameter as opposed to the 2.5 meter mirror of the Hubble Space Telescope. So I'm actually fairly intimately involved in this project, as is Al here. And let me tell you a goofy story that will illustrate what it's like to be involved in this project. So a number of years ago, this project hit a problem with the budget, in that it turned out that this thing was going to cost about twice what we thought it would cost. And this thing is a multi-billion-dollar mission. Okay, so what NASA did is they convened a special committee of astronomers from all of the participant countries, and one of those participant countries, I'm happy to tell you, is Canada. Okay, so we are involved in this mission at a small but very, very significant level. I was Canada's representative, and so I was, shipped off to Baltimore and Washington, D.C. to sit on all these kind of high-level committees. And one aspect of this is that this telescope looks pretty complicated. And it is pretty complicated, and apparently it uses all of these kind of hyper-secret military technologies, right? And as a result, whenever the discussion moved towards the area of the hyper-secret military technologies, Bob the Canadian was asked to get up and leave the room. Okay, because we are not, privy to the secrets of the hyper-secret military technologies. So I'd get up and leave the room. So the most hyper-secret military technology of all, the one that if you understood, you would be a gnat's whisker away from being able to manufacture your own nuclear bomb or something, was how the primary mirror of the James Webb Space Telescope is actually made. It's made of this complicated beryllium alloy, and it's carefully machined and stuff. And so whenever discussion roamed even to the general vicinity of this topic, Bob was outside smoking a cigarette in the corridor. Okay, so I got back to Toronto and I'm like, man, I'm depressed. I sure hope these Americans know, what they're doing, and I cannot, really have an opinion because all the interesting hyper-secret stuff is just, we're assuming it's going to work. But I thought, what the heck? I try and find out about this hyper-secret military technology because, I'm a professor and I'm supposed to be a curious guy. So I type, how is JWST's mirror being made, into Google, and I get directed to YouTube, and I see this. Okay, so if you want to know, if for some reason this is important to you, you know exactly what it's made of. You can see exactly how the alloy is prepared. You can see how it's machined. You can see every detail, okay? Yeah, so now after this, you have to sign some documents. Okay, so So why are we doing this? Why are we doing this? Okay, so behold mankind's deepest vista into the cosmos using the present generation ultra best telescope out there, the Hubble Space Telescope. This is the Hubble Deep Field, okay? So this is mankind's, along with similar other things called, so this is the Hubble Deep Field, there's the Ultra Deep Field, whatever. This is what you get when you take the Hubble Space Telescope and you point at a single point on the sky, and you open the shutter and you just wait a week and you collect all the light from the most distant objects. This is as far as humanity can look. These galaxies are born soon after the Big Bang, and they're very far away. But are they far enough away to tell us about first light? No. Okay, using the precise measurements of the most faint objects detected in the most extreme experiments astronomers have been able to devise, we are not going nearly deep enough, we are not seeing nearly far enough to see the sources of first light. The Hubble Space Telescope just isn't good enough. If you compare this with what you're going to get with the James Webb Space Telescope, this is the exact same thing. This is a simulation, okay? So this is not reality. This is somebody plugging into their computer some assumptions about what first light might be and how bright it'll be and stuff. But if you plug in that simulation, you get this. And it turns out that this is deep enough to see things that are at least conceivably the first stars collected into the first galaxies. And this is a comparison showing the Hubble Space Telescope, actual data on top, and what a simulation of what it should look like with the James Webb Space Telescope on the bottom. Okay, so what we need is to have a better space telescope if we're to have any hope of doing this directly and finding the sources of first light. The very faintest things you see in the simulation at the bottom should correspond to proto-galaxies made up of these population 3 stars, which we don't understand very well, and they should be enough to do the job of setting in motion this chain of events that leads to the complicated universe you see around you. So that's exciting, okay? But there's a problem, and the problem is it's going to take another 5 freaking years to get the answer if this is the case, right? Because this thing doesn't get launched till 2015. I am not a patient guy. 5 years is eternity for me, right? There's no way I can wait 5 years and not know the answer to this. So even though there's huge progress in the last year, what I want to know is there some way to get there before JWST is launched, the James Webb Space Telescope is launched? And it turns out that there's some hope that we can do that, okay? But we have to cheat. We have to cheat like crazy. Okay, so I'm going to describe 3 ways that you can combine to cheat like crazy and maybe get the answer next year, not in 2015. So the first thing you can do to cheat like crazy is you can use something that Einstein taught us. Okay, so Einstein taught us that you shouldn't think about space and time as being separate things. You should think of them as being linked together in this thing called space-time. And the cool thing about space-time is that it is distorted and bent by mass. So if you have if I put a black hole here or something incredibly massive right here, what it would do is bend space and time around it. And what it would also do, as part of this process, is bend light. Okay, so if I have a laser pointer, if I had one that actually worked, okay, I would shoot it out here and it would get bent by this mass here. Okay, so I'm bending light rays. So what else bends light rays? Well, my glasses are bending light rays. This thing is bending light rays. This is a telescope, right? So you can use huge collections of mass as telescopes. So what out there is massive enough to bend enough light to use it as a telescope? Well, it turns out that galaxies, and more to the point, large collections of galaxies, will do the job. Okay, so this is called gravitational lensing. And this is an example of a gravitational lens. So what is shown here, okay, is a collection of galaxies. And if you look at the thing labeled 6.8 there at the top left, what that is a very, very distant galaxy whose light is being bent and amplified by the galaxies in front of it. So this is nature's telescope. And if you look at the 2 things circled up there, those little ellipses labeled A and B, those things would be completely undetectable if we weren't using this cheat, if we weren't using these galaxies in the foreground to amplify them in the background. But we can see them, and we can see them because we are using nature to amplify and lens light from the distant things behind it. So that's a great cheat, okay? So we can use that. You look like you want something. The clicker. Oh, you want the clicker. Okay, no need to whisper. It's an intimate audience.
Just check the laser pointer because
Okay.
it was working.
It's probably been turned off. Anyway, okay, so that's the first cheat. So we can, if we look, oh man,
It's got to push and hold. It takes a couple seconds.
push and hold.
The laser button, yeah.
Okay, how can I hope to build a space telescope? I can't even Okay, apparently you got to push and hold it for a few seconds. All right. Okay, so these guys here, okay, no way you would see them, all right, if it weren't for these guys here bending their light behind it, in front of it and acting like a telescope. Okay, so that's one cheat. And so one guy who's been cheating like crazy and who's my inspiration is kind of my mentor, this guy here, Richard Ellis at Caltech, who has abused the Keck telescope incredibly. He was at the time the director and basically said, all the time is mine. I'm going to use all the time for my science. And he did this and detected these little smudges using this trick. Okay, and these little smudges turn out to be arguably, because we're not sure, very distant objects that, and he actually got on cover of Time magazine for this, the dog, that may be, the first galaxies. But the problem is it's not a very efficient technique, and these results have not yet been confirmed, okay, because this is just so hard to do. So really what you'd want to do is to apply this technique in a smarter way. And this is where your taxpayer dollars become important again, okay? Because it turns out that you guys are paying for me and Al to do this in a way that is 100 times more efficient than anything that's ever been tried before. And this is all part of a survey that is just beginning, and we'll be taking data for the first time, I guess inside of a year, called the Gemini Genesis Survey. And what it looks like, well, how it works is it relies on a device, an example of which will be outside after this, right? Is this true? Am I telling the truth? You guys have solar telescopes set up, right? Okay, so you have solar telescopes set up. So go outside after this talk, and you will see a solar telescope looking much like this. And in the heart of this solar telescope, if you took this thing apart, which you won't want to do, because the owner will be mad, but if you did, okay, you would see inside of it 2 tiny little circles of glass pressed tightly together. That's called a Fabry-Perot etalon, and it was invented by these French guys about 100 years ago. What these French guys worked out was that if you take 2 pieces of very, very carefully polished, finely flat glass and you push them together, it operates as a filter. It only passes very, very specific wavelengths of light. So this is a great thing. Okay, it's so great that Canada, using the enormous brain of Al Scott sitting here, okay, is building one of these devices. And so you could think of it conceptually as looking like this, taking the James Webb Space Telescope and putting one of these in front of it. That's effectively what it's, well, no. You have to have the flag too, obviously. No good without the flag. Okay, so this is called a tunable filter imager, and here's what it really looks like. So everything shown in colors here is being supplied by Canada. This actually fills me with enormous pride. I don't know why, I'm not much of a flag-waving person, but when I look at this, I am so proud that Canada is able to build this thing. And the heart of it, if you look, are these 2 pieces of glass pushed tightly together. So what it occurred to me and Al is that we could take these 2 pieces of glass, which Canada has developed the technology to manufacture and keep precisely aligned, and steal that technology and use it on a large telescope from the ground rather than just from space, and attempt to look for these first galaxies 5 years ahead of the James Webb Space Telescope. So this is the heart of the plan. Okay, so this is the additional cheat you need. Remember, the first cheat was a gravitational lens to amplify the background light. The next thing is to clone the James Webb Space Telescope's tunable filter imager. It's called the Flamingos 2 tandem tunable filter, and it looks like this, and it's sitting in the basement of the astrophysics building at the University of Toronto, and use that to try and look for the sources of first light. But would that work? Is that enough? No, okay? You still need to cheat in other ways in order to succeed. So here's the next cheat, and this in some ways is the hardest cheat of all. So our life-giving atmosphere that is responsible for all the good things on Earth is the enemy to astronomers. Okay, so if you look at stars with a large telescope, they look like this. What you want them to look like is this. So what happens is that the twinkling of starlight is actually distortion caused by Earth's atmosphere, which makes everything blurry. This is the main reason why you launch a space telescope, to get above Earth's atmosphere, to get above these distortions. But there's another way to get past these distortions, and that is cheat number 3, and that is to use a laser. So this is a technology known as adaptive optics that is in its infancy. And the idea is you shoot a laser up, 80 kilometers up from ground level. There's a layer of sodium atoms caused by meteorites that hits Earth's atmosphere and then break apart. So there's this sodium, and then you illuminate it with a laser. It looks like a star when you hit it with a laser, and you can reverse the effects of Earth's atmosphere's distortions to make it look like you're in space. The view will look like you're in space. This sounds pretty complicated, and oh boy, it is. However, after years and years of effort, such systems are actually more than a fantasy, they're actually working. So I'm going to show you an animation of how it's going to work. This is an active system known as Altair on the Gemini North Telescope. Canada is involved in this. So here we are on the island of Mauna Kea. We shoot the laser up. Obviously this is in slow motion. Okay, it hits this layer of sodium atoms from the meteorites. Then we go back down, and what it looks like to us from the ground is a bright star. So here we are atop Mauna Kea again. The light enters the Gemini telescope, and at this point it's all distorted. So that's bad. So our mission is to make this distorted light into perfect light, like you were in space. Okay, so what happens here is that distorted light enters into this system, and it hits this thing called a deformable mirror, which is actually floppy. Okay, so here's the distorted light, and you can see it's all bent and horrible. It looks like a potato chip. So what you do is you distort this mirror to give it the negative of the distortion caused by Earth's atmosphere, and what emerges then is the star looking as if you were out in space. So why do you believe it should work? Well, because I'm not going to show you images, okay, of this system in action. This is Jupiter's moon Io, as imaged by the Voyager spacecraft. So we actually took something from Earth, built it, launched it to Jupiter. It zipped by Jupiter, took a bunch of pictures of this satellite of Jupiter. That's what it looks like. This is what Io looks like with a telescope from the ground without adaptive optics, without any of this fancy technology. This is what it looks like when you turn the adaptive optics system on. Now, how cool is that? Basically, using a telescope on Earth, you can get something that looks almost as good as a spacecraft by using adaptive optics. Another example, this is Neptune, seen with and without adaptive optics. So this is what you see without this adaptive optics fancy technique. This is what you see when you turn it on. Again, it looks kind of similar to what you get from a spacecraft that's zipping by it. This is a simulation now, okay, because all this technology is so new, people are only now beginning to turn it to galaxies. But in about a year's time, this is what we expect to happen. This is what a galaxy looks like at present with that telescope. This is what that galaxy is expected to look like inside of a year. Okay, so this is more or less the view that you would get from space. Now this is a limited technique. It only works over a limited range of wavelengths. It only works over tiny patches of sky. In no way is it a replacement for the James Webb Space Telescope, but what it does do is in this kind of limited way, maybe let you get there ahead of the James Webb Space Telescope in a small way, okay? So, we're going to do this inside of a year. What are we going to find? Well, nobody knows. That's the fun of this. That's the fun of working in the frontier. But I don't let this kind of ignorance stop me. So what I do is I walk across the hall to a theorist, because I'm an observer, and I say, "Dear Mr. Theorist, what am I going to find?" And they say, "Oh, well, I'll just plug it into my computer and do a simulation." And so this is a computer simulation of the formation of population 3 stars. Okay, and this theorist tells me that basically we zoom in through these regions of neutral hydrogen and helium, and at the base of it, we will see a supermassive star. So if I take this a step further and I ask the theorist what I'm going to see at the end of the day, he says, what you're going to see is something like this. This star is going to die. So this is a star 200 times as massive as the sun. And when it dies, it's going to go immediately into a black hole. Okay, and that's why we don't see these stars in the nearby universe. It becomes a black hole instantaneously. And here's where the theorist is wrong, okay? Because this is a simulation done a year ago. Now watch what happens. It goes boom in my theorist friend's computer. And we now know this doesn't happen. Okay, because I drew the red line across the thing. That's what we've now eliminated. So what's the lesson? The lesson is, what we're going to find is not something that anybody can tell me in advance. Really what we're going to find is unknown. This is the lesson of observational astronomy. Whenever you build something and you explore an area of the universe that is unexplored, what you find is deeply mysterious. So we don't know what first light is, but I bet you, and I bet a lot, it's not going to be something that anybody predicts in advance. So we got to go out there and look. At least we know where to look, though. Okay, so this is a numerical simulation which at least lets us plan our experiment. So, and these theorists are incredibly useful for helping plan these experiments. So that's what these guys have done. Okay, is they've said, okay, Bob, what we're going to do is we're going to populate a box of the universe full of these first light objects, and we're going to see how the universe changes with time, and that's going to help you design your experiment better so that you can do it in the most efficient way. So this is what we're doing. Okay, so a year from now, we're using insight gained from these n-body simulations, numerical simulations, to help us design our first light experiment. So let's say this all works. Okay, so let's say a year from now, I'm able to talk in front of a public audience and explain to them the nature of first light. What happens next? Well, 4 years after that, the James Webb Space Telescope gets launched. And it ought to do a far, far better job than what we're able to do now. But then what happens? The problem is these things are going to be incredibly faint. So even the James Webb Space Telescope, with all of its power, is not going to enable us to learn very much about these things other than the basics. And it turns out if you want to learn more about these things, you've got to take it to the next level. And the next level is something called a 30-meter telescope that, oh, I have to do something important. Okay. It turns out that the 30-meter telescope, which is something that Canada is deeply involved in, and if all of the stars align in their appropriate way, will be appearing on a mountain near you on Earth about the year 2020, is really what's needed in order to characterize these things. Because what you really want to do is to take a spectrum of one of these things to work out how much hydrogen and helium are in these things, to verify that there really are no other chemical elements, that they really are generation zero, the very first things that formed. And in order to do that, no space telescope is going to be big enough. And so really what you need to do is to build something on Earth. And the thing that we're hoping to build on Earth is shown here. So Canada is involved in this at a 20% level. This is a $1 billion project. It's incredibly exciting. If there are any high school students in the audience, or even there's like a young girl, I hope that you grow up and become involved in this kind of thing. Because that's the main message I want to leave you with, okay? Is that you're living in an exciting time where we're learning so much. But the main thing we've learned is that we don't know anything. Right? The universe is this fantastically mysterious place, and even with the tremendous pace of progress of the last few years, we're nowhere near finding out the limits of even these fundamental things. What set in motion the complexity of the universe? What makes up most of the universe? All of these things are questions that we are just beginning to grope our way towards finding answers for. I see no end in sight. It's a very exciting time, and if you're looking for something to do with your life, I can't think of anything as exciting if you're a Canadian and wish to get involved in as this 30-meter telescope. I hope it happens, and I hope we see it quite soon. And I'll stop there. Thanks very much.
Thank you very much. I think we all have an idea of why Dr. Abraham won that teaching award, so it was fantastic. And makes your analogy, I think we'll all be thinking a little bit differently about plasma than we did previously. Things you learn at Oxford. Okay. All right, so at this point we have some time for some questions from the audience. Maybe I'll pass the mic back to Dr. Abraham and take a few.
Sure. Hey.
What was the nature of the universe in the time before first light?
Okay, so the question is, can you guys hear the questions? Can you guys hear the questions in the front from the back? No. Okay. So the question is, what was the nature of the universe in the time before the Big Bang? So this is first light, time before first light. So this is the cosmic dark age.
After the Big Bang.
Okay, so the Big Bang occurs. It's the most boring universe imaginable. It's just the stuff in that bottle. It's hydrogen and helium. No stars, devoid of any complexity. It's just the stuff in that bottle. It's a boring gas. And somehow uniform with perhaps tiny little fluctuations, which you can see the imprint of in the cosmic microwave background. But a dull, boring universe. The universe's mission is to go from that dull, boring universe to the exciting universe you see around you, and you need first light to catalyze that process. So it's a dull universe. That's why they call it the cosmic dark age. It's just dull.
And about 250 million.
250 million years after the Big Bang. Go for it.
What wavelengths will the Webb Space Telescope pick up?
Oh, so the question is, what wavelengths will the Webb Space Telescope pick up? And the answer is it's going to operate in the near and mid-infrared. So wavelengths, redward of the wavelengths you pick up with your eyeballs, which is a decision that was made largely to save money. Originally, it was going to be made to work at a longer range of wavelengths, but I won't bore you with the details. But that was one money-saving maneuver that was decided upon to try and have it focus on just the infrared.
Deep?
No, it's just the near infrared.
What was there before the Big Bang?
Oh, I love that question. Okay, in fact, that's what I thought you were asking. Okay, so the question is, what was there before the Big Bang? And you know what's funny about this question, okay, is, so this kind of broaches upon the, what is cosmology, what is theology question, where is religion, where is science, etc. And so I will give you the answer that I was instructed to give you in graduate school to that question. Okay, so the answer I'm instructed to give you is this. It's not a fair question. All right. Why is it not a fair question? Because the Big Bang created time. All right. So it's almost a tautology to say, so at the Big Bang created time, ergo there is no time before the Big Bang. So that's I think that answer is a little too cute. Do you think it's? Do you walk away satisfied with that answer? No, me neither. Okay. And so here's the problem. Okay, so this is a problem that scientists are groping with now. We almost have a complex about it, okay? Because it turns out that we have gone from that pat answer, which I happily deliver, to asking ourselves whether or not that's a reasonable way to address that. And the reason is because we're sort of redefining, and I'm not happy about this, but it's what's going on. We're redefining what science means. So what I tell my students is that the hallmark of science is this thing called falsifiability. I'm supposed to, whatever I do, I have to be able to prove it wrong. So since I can't go back, even in principle, to a time before the creation of the universe, it's not science. I'm not allowed to speculate on it. But it also turns out that there are theories now, such as string theory, which basically say our universe is one universe in a sea of alternative universes which exist in separate pockets of space and time. So therefore, if I believe in string theory, I'm actually allowed to ask about stuff that happens outside of our universe, which is why people, of which I am an example, wonder whether string theory is a proper science. Okay, so a string theorist would very happily stand up here and attempt to give you an answer. And what I'm telling you is I gave you the answer I was instructed to give you, but I'm also telling you that there are people out there, you know, with PhDs in theoretical physics that are now telling me they can attempt to answer such questions. And I personally think that, you know, Florida swampland is what they should be selling, but other people disagree. So it's interesting. That question is now at the interface of real science and pseudoscience. Hey.
You spoke of first light a moment. It works, didn't it?
Yeah, it's loud.
You spoke of first light a moment ago as an effect. The question to you, and what was before first light? And so, you needed first light, and then all these other things happened. And you spoke of a kind of the dull place of
Yes.
hydrogen and helium.
Yes.
But it seems to me that the first light is not a cause, it's an effect. And the real question is where the hydrogen and helium come from, that it went to, they started to get their act together soon, et cetera, et cetera. I wonder how some of these theories you speak of, the string theory, multiverse theory, 11 dimensions, all that good stuff. Is there any middle of the road thread that's being found through all of that? Or?
No, and so I'm kind of with you in casting a skeptical eye on that stuff. And the reason is that we are nowhere near being able to test predictions made by such theories. So string theory is sort of the poster boy. Well, first of all, let me preface everything. So I'm about to try to rubbish string theory, but let me try and defend it before I try and rubbish it. Okay, so it's the best thing going for theories which attempt to unify the force of gravity with the other forces of nature. There's no, it has a number of very, very elegant things that seem to bring these things together, and we know that's something that has to happen. So somewhere out there is a theory that unifies these forces of nature, and we're attempting to find one, and string theory is the best one going.
Are you sure about that?
No, I'm not sure, but yeah, I'm pretty sure. Let me give you an example of why, because it's worked before. I'm the sort of guy that basically says it worked before. Let's just do it again. Okay, so Einstein unified electricity and magnetism, showed it was one force, electromagnetism. Afterwards, this weak force was unified with electricity and magnetism, and so there's actually one force that is all three, and so. There's this thing that led to structure in the universe that there's pretty good evidence for now called inflation, that basically unifies a strong force with the other one. So the only one left out is gravity. So there's sort of almost a bias, an aesthetic bias, that if you're going to have some number in the universe of something, that number should be 0, 1, or infinity. Right? And so 0, obviously there are forces. There don't appear to be an infinite number of forces, so probably there's one force. Otherwise you would have gravity and everything else, and that seems kind of inelegant. But in any case, it looks like there's no middle ground, because there's no easy way, there's no even conceivable way to test any of this stuff in a lab. And the closest you can do is do what we do, which is to use the universe itself as a big lab, right? And you can go and look very, very far away, very early on in the history of the universe and see all this stuff happening. But the problem is you've only got one of those, right? We've only got our universe. So it's not like you can run the experiment many times and then change the universe each time and see what happens. So it means that in terms of doing the regular sorts of science, you can't do it. You just basically have to go with our universe the way it is and try and understand it. And in order to do this, we are like 100 orders of magnitude away from being able to explore the appropriate energy scales of the Big Bang. So we're just, I can't even imagine a century from now, any experiment testing stuff in a laboratory that will let us probe string theory. It's inconceivable to me. And so in the meantime, how do you make progress? So you either close up shop or you allow these string theorists to speculate. And I'm happy for them to speculate, but I just think we ought to be skeptical at the same time.
I'll just ask one more quick question. Hawking.
Stephen Hawking, yeah.
Hawking talks about just the possibility that maybe there is no one great unified theory. In fact, what you get is a whole bunch of little patches that kind of maybe they match together in certain circumstances, certain times and places, but not in any kind of universal way.
Yeah.
And it's only when you kind of massage that whole thing together, it comes out with like a powerful shape or something.
Yep.
And that's where we're ever going to find it.
Yep, let me explain this, because maybe people don't know what's going on. Let me explain this. And so yes, that's entirely right. That's what Hawking thinks, and in fact, that's what a lot of people think. So here we are, we're living in this universe, and the universe has got these properties, okay? And the properties of the universe are vast, but you can kind of refine them down to just a few important ones. So there's a book, for example, called Just Six Numbers, written by Lord Martin Rees, okay? It's a fantastic book. And he shows that there are these 6 numbers that basically govern almost all properties in the observable universe. So these numbers are, for example, the ratio of the strength of the force of gravity to the force of electromagnetism. Another example of a number is the ratio of the mass of the proton to the mass of the electron. And anyway, there are these 6 numbers. Now, the interesting thing is, if you take these numbers and you change them by just a little bit, by like 0.001% in some cases, what emerges is a universe that cannot sustain life. No way. So if you change the ratio of the mass of the proton to the mass of the electron, what you would get is a universe without stable atoms. If you change the dimensionality of the universe, so that we have 3 spatial dimensions and 1 time dimension. You say, why? Why can't we have 11 dimensions like string theory? It turns out that only a few of those result in stable orbits for planets moving around stars. So our universe looks like, in this picture, it's been fine-tuned, right? It looks like, if these numbers were different by just a tiny little bit, there would be no life. So the universe that we see around us couldn't exist. So then you say, if you're religious, you say, I have an explanation for that, right? The creator of the universe created the universe with precisely the values required in order for life to emerge. But if you're scientific, or at least if you're unhappy with that explanation, you look for alternatives. And one alternative is that basically the universe that we see around us is just one of 10 to the 100 other universes, all of which have different values of these parameters. And it's only those tiny little sub-universes in which, just by random chance, those values happen to be ones from which life could possibly emerge, that life exists in order to ask questions about the universe. So let's say the universe has got all these different little patches. If you're in that patch over there, life couldn't emerge. Obviously, there would be nobody in that patch asking about the nature of the universe. So this is called the anthropic principle. Okay, actually it's called the weak anthropic principle. We are here just because of dumb luck, right? And the properties of the universe are what they are just because of dumb luck. So I find that incredibly unsatisfying as an explanation. Right? So I'm not very religious. I don't like that explanation either. I don't like the anthropic principle, and so I'm left saying, I don't know. Okay? But that is the nature of this particular explanation, that the universe has got all of these little weird patches. You're rolling the dice in every single one. Once in a while, you get exactly the right parameters, and you get a universe with life. And so that's why the properties of our universe are set the way they are. So it kind of stinks if ultimately I spend my entire life trying to understand the laws of the universe, and it turns out it's just dumb luck. So that's why I don't like that explanation. Okay, sure.
Just a few minutes ago, you mentioned that the unification of the strong force is somewhat tied to inflation, I think you said.
Well, the inflaton field. So I oversimplified in one sense. So there's this thing called inflation, which I don't think I have time to explain. Okay, but soon after the Big Bang, the universe became like 10 to the 28 times bigger in a tiny fraction of a second. Like, it became enormously bigger. And the explanation for that at the moment is it was caused by forces of nature that had been unified before breaking apart and becoming distinct. And people argue about what force it is that separated it out and became distinct. And one possibility is it's this strong force, which I also don't have time to explain. But anyway, that's the idea. Is there's this thing called inflation. The universe became vastly bigger soon after the Big Bang, and it explains a lot of stuff. Sure.
How do you think the discovery of the Higgs boson particle, the so-called God particle, how do you think that could affect the direction that astronomy is going in?
Okay, so you guys hear the question in the back? Okay, so there's this thing which I showed a picture of, okay, a detector for, called the Large Hadron Collider, which is I think possibly certainly the biggest particle accelerator that's ever been constructed, and arguably the biggest that's ever going to be constructed, and it's being completed outside Switzerland, should be turned on like next year. And you know, the main thing people point their fingers to that they hope this thing will find is a particle called the Higgs boson, and this is a particle that essentially gives the property of mass. Okay, so if this thing is found, the question is, you know, let's say this thing is found, how is it going to affect the future direction of astronomy? And my answer is to, you know, probably not very much to begin with. The reason being that everybody's assuming it's going to be found. Okay, so it's the Higgs particle is a counterpart to a couple of other particles that have already been found, and people would be astonished if this thing wasn't found at some level. So what I would say is, if this thing is not found, it would actually be more surprising, and the ramifications there would be more important for astronomy. So if this thing is not found, it's telling us that our ideas for the nature of how things get their mass are wrong. And that, I think, would be more profound. So I hope nobody finds anything, in which case we don't understand stuff, and that's always a good thing. It leads to more insight. Go for it.
The black holes, do you use transformation like perpetuum mobile like that?
I'm sorry, I couldn't hear that.
The black holes are like a perpetuum mobile.
Oh, perpetual? Okay, so the question is a black hole a perpetual motion thing? The answer is no. So, okay, hands up everybody who doesn't know what a black hole is. Quite a few. Okay, so I'm going to explain it. So here's what a black hole is. Remember how I said earlier that Einstein said that there's, you know, space and time are linked together, this thing called space-time, and mass bends space-time. And so if you have mass, it'll bend light. So if there's enough mass, right, then what's going to happen is that light, rather than just being bent, is going to get caught, right? So no light will emerge. So it's sort of like this. What can I abuse from Carleton University? Can I borrow your mouse for an important scientific demonstration?
Absolutely.
Okay. All right. Okay, I just unplugged. Okay, I'm going to use your USB key for my important scientific demonstration. Okay, so I've got the USB key here, and so I'm going to throw it up. Now, observe what happens. It comes down. All right. Now, what would happen if I took this USB key and instead of throwing it up at my pathetic few meters per second, I threw it up instead at 100,000 kilometers a second? All right. This thing would get launched and keep going. Okay. So escape velocity for Earth is like, I'm going to betray imperial units. It's 25,000 miles an hour, right? So whatever that is in kilometers, 12 kilometers a second. Okay, 12 kilometers a second. So this thing, we're going 12 kilometers a second, it would leave Earth forever, right? So if Earth were way more massive, all right, I would have to throw this thing way faster in order to get it to leave the Earth. So eventually, I could make the thing so massive that I would have to throw this thing faster than the speed of light in order to get it to leave the Earth. Now, Einstein taught us that nothing can move faster than the speed of light, so that light can never escape. So what that means is basically I have got so much mass that light can never leave something, and in Einstein's general theory of relativity, what that means is you've basically got your own little sub-universe. You've cut that universe off from everything else, and that's what a black hole is. Okay, it's a collection of mass that it's so dense that light can't emerge from it, and so it's basically cut off from the rest of the universe. And in terms of perpetual motion, I think it's not really too linked, although it has thermodynamics detail. That's what a black hole is. Go for it.
Forgive me if I missed it in your presentation, but what was the trigger event, the event that had to happen, the critical event that had to happen to trigger that reionization that you were talking about earlier? Or maybe another way of asking this is like, what were like the necessary preconditions?
Okay, so the question is kind of a deep one, which I'm going to give you a pathetic answer to. So the question is, what were the necessary preconditions to trigger this reionization? And the necessary precondition is just a bunch of energy getting dumped into the universe. That's it. So you can dump that energy any way you want. You could dump it in weird elementary particles decaying. You could dump it in first stars shining. You could have electromagnetic energy emerging from stuff falling into black holes. It doesn't matter. Anything that dumps energy into the universe is going to be sufficient, if there's enough of it and enough energy, to cause this hydrogen gas to split apart and become a hydrogen plasma and set the thing going. And that's the coolness of it, is we don't know. Right? We now know kind of when it happened, but we don't know what happened. And so I give you the most pathetic answer, which is we know something happened to set this thing going on, but we don't know what. And that's the whole point of building these telescopes, is to try and figure out what. And it'll be really annoying if, having gone to this extreme of trying to build the James Webb Space Telescope and the 30-meter telescope, we find nothing. Because it'll be depressing and also very cool, because it'll mean that it's something even beyond anything we could conceive of. But we're designing these telescopes with the express purpose of trying to find it, given almost any alternative. So any kind of collection of population 3 stars, we ought to be able to pick it up. If it's stuff blowing up, but with properties beyond which we have seen with these satellites, we ought to be able to pick it up. So for almost anything you can envision, we'll be able to pick it up. But you know what? We can't envision everything. So something happened, we don't know what. Stand by. 2015 will give you our best answer. And if 2016 we still don't know, I think we're going to have to build another telescope.
I'm not more of a that's a gold question, but that narrowband filter, the
Yeah.
Pro filter, why do you need it, and what wavelength is it looking at?
Okay, so the nuts and bolts question is, how is this magic filter going to work? So it turns out that, and why do you need it at all? So a good model for the first stars, these population 3 stars, is that they give off most of their energy at one narrow wavelength, corresponding to one emission line called Lyman alpha, which is the ground state of hydrogen to its first excited state. So something like, in most models, something like half of all of the energy being emitted by these things, so the light energy being emitted by these things, comes off at that one narrow wavelength. So the idea is, if you can take this filter and just look at that one narrow wavelength, then you should be able to see these things with much greater contrast than if you looked over a huge range of wavelengths. So that's the idea. And if that theory is wrong, then this filter is not going to work. Well, the filter will work fine, because Al, of course, being a genius, built it to work. But nature may not cooperate, and most of that energy may not be coming out in that line, in which case we're not going to find anything. Go for it.
Can you speculate whether the dark matter, dark energy existed prior to the ionization formation of plasma, or is it a consequence?
Okay, actually, that's a good question. Okay, so the question is, did dark matter and dark energy exist prior to this epoch of reionization? And the answer is, dark matter for sure existed, but dark energy didn't. Okay, hold on, let me back up here. Hands up, everybody who doesn't know what dark matter and dark energy are. I think that this should be taught at kindergarten level. It's so fundamental. Okay, so this is my opportunity to tell you about this fantastic new development in astronomy. Okay, so here's an amazing thing. 97% of the universe is not made up of visible stuff. Okay, so 97% of the universe is not energy as we know it, Jim. 97% of the universe is not made up of atoms, okay, or light. 97% of the universe is mysterious. So this mysterious stuff, okay, gets broken into. So one of these things is called dark matter. So what dark matter is basically a source of gravity. So we know, again, I keep saying it, gravity bends space and time. So we can weigh galaxies, and we see by weighing them using gravity that they are made up of way more stuff than you can see, right? So I look at a galaxy, and it's although I see beautiful spiral arms and stuff, really what's out there is 10 times as much stuff as you actually see in that galaxy. So that's stuff you call dark matter. So, that was pretty darn mysterious, and explaining dark matter was viewed as, the most important thing that one could do with one's career prior to reionization for a long time, right? And then what happened was in 1997, another component of the universe was discovered, which turned out to not be associated with gravity, but to be associated with the expansion of the universe itself. So Einstein in I'm going to make up the number, it might be wrong by a year, but anyway, 1925, Einstein, coming up with his general theory of relativity, noticed that his theory predicted an expanding universe. And this being 1925, and prior to Hubble doing his thing and discovering the expanding universe, Einstein thought this was crazy. And so he added an additional term to his theory that balanced the universe out, as basically an anti-gravity sort of thing that stopped the universe from expanding. And then like the next year, Hubble discovered that the universe was expanding, and Einstein went, "This is my greatest blunder, This is my big screw up of my career. This is his big opportunity to predict the expansion of the universe, and he blew it." But it turns out that Einstein is such a genius that even his screw-ups turn out to be right, Because in 1997, what was discovered is that this extra component in Einstein's theory, this so-called anti-gravity term, actually exists, right? And this thing is associated with the vacuum itself. So as the universe gets bigger, there's more vacuum, and so there's more dark energy. That's what this term has come to be known. Because remember, when you don't understand something, what do? Give it a name. So that's what the name that was given to this, dark energy, all right? It was similar with dark matter. We have no clue what it is, but dark matter, oh, it's dark matter. You feel better. So that's what dark energy is. It's an additional component to Einstein's general theory of relativity that acts like an anti-gravity on large scale, and as the universe gets bigger, there's more vacuum. And this term is associated with the vacuum. So to answer the question, at the epoch of reionization, the universe was much smaller. So there was relatively little vacuum, so there wasn't very much dark energy. So at that time, there was lots of dark matter, because that's associated with the universe itself, but there was very little dark energy because the universe was so small. So one of those two things mattered, and the other one didn't. Any other questions? I'm happy to do Q&A forever, so you stop me when you want me to stop. Okay.
I think it was in the April Scientific American, there was a cover story that suggested that if you discard the Copernican principle that we're in an ordinary part of the universe, but we're in a special part of the universe, you can dispense with the idea of dark energy, and the problem disappears.
Yeah, that's true.
Seriously?
Not by me. So here's the thing. So there's one of these, there are these philosophical principles by which scientists live their lives, right? And one of them is, so let me restate the question. Do we need these fancy things like dark matter and dark energy if I'm willing to, toss out my fundamental beliefs and principles upon which I hang my science? One of which is called the Copernican principle, which is that we do not live the Copernican principle is we live in basically a typical bit of the universe. It's often called the cosmological principle as well. That basically we're not special. Right? We don't live in a unique universe. We're just basically in a typical Earth-like planet orbiting a typical star in a typical galaxy in a typical patch of the universe. So if I'm willing to chuck that out and say we're special, then do I need all of this other stuff like dark matter and dark energy? And the answer is maybe not. But then I'm almost repulsed by the very thought. right? Because if I toss out the the idea that we're not special, then anything goes, right? I can't explain anything. I can say that basically the laws of the universe are what they are because basically it's just kind of randomness again, and it's the anthropic principle. It's the same way of stating it, right? And so the argument there is that we see this dark energy thing because our little patch of the universe just happens to be expanding for whatever reason, right? And if I looked at another patch of a different universe, it would be contracting for whatever reason. And it just kind of, so our patch is special. It's an expanding patch. But on a larger scale, the universe isn't expanding or contracting, it's kind of just static. And it's just because we happen to live in this special patch do we see it doing what it's doing. And it's logically totally consistent, but I find it philosophically repugnant. Now, the universe doesn't have to obey my sense of the philosophical aesthetic, right? But it does basically mean that you would have to run your science by different rules, or at least redefine what you take to be kind of ground zero and axiomatic.
We have time for maybe one more question.
Kind of a theoretical question. We know what absolute zero is. Do we know what absolute hot is?
Is there a ultimate? Okay, so the question is absolute zero is the coldest you can make anything. Okay, it's the temperature at which there's no motion. So temperature is basically just a measure of how fast stuff is moving. So if nothing is moving at all, that's absolute zero. And by the way, that's impossible because of quantum mechanics. It says everything. Anyway, never mind. So the question is there some in principle limit at which something can be the highest temperature? And as far as I'm aware, the answer is no. I guess, well, hold on. So I guess what you could say is if you take the entire mass of the universe and use E equals mc squared, and you get a certain amount of energy, then I guess what you could say is in principle, nothing can have more energy than the total energy content of the universe itself, which sets some absolute temperature. But obviously it's kind of out there. But that, at least in principle, I guess would be the hottest something could be.
What's the hottest temperature ever recorded?
Hottest temperature ever recorded? I'm afraid I don't know. I know how people kind of do this stuff with particle accelerators crashing stuff against other things. And the highest energy people are achieving there is approaching 1 tera electron volt. So that's the highest energy achieved in a lab. And so to work out the corresponding temperature, you'd need to know the mass of the particle and do some division.
How does that translate into Kelvin? What would be a Kelvin number?
Oh, incredibly hot. Really hot. Certainly billions of, I would say billions of degrees. Okay, and so the interior of a star, nuclear fusion, people are messing about with fusion. That requires temperatures, in the tens of millions of degrees. And this is way hotter than that. Millions for fusion. So up to like 100 million degrees for fusion. So pretty darn hard. But they don't last very long, at least not in the lab. They do in a star though. Okay, so is that it?
Yeah, I think we're...
Okay, thank you very much.
Okay, so just on behalf of the Ottawa Center RASC, we'd like to extend our appreciation for you coming out here and helping celebrate IYA with us here in Ottawa. And just as a token of our appreciation, we have a little something here for you.
Oh, wow, thank you.
So again, just another round of applause for Dr. Williams. We now go into our musical part of the program. And just to show that we amateur astronomers are multi-talented lot, we have our very own Rob Alexander and Albie Goranson, who are going to give us a musical of astronomical interlude. And
I wrote this song for Kent, who's the owner of Focus Scientific, for Christmas a couple of years ago, and it's called Stargazing, and it's kind of a special song. It's all about sort of falling in love with the sky and just what's out there, the mystery and the magic of the night sky. We're, as a matter of fact, Focus Scientific we're having a brand new store. We're moving to a brand new store. So we hope, we'll see
This
you
month?
guys there. Yeah, this month. It's 911 Carling Avenue. And yeah, we hope we'll see some of you guys there. And I just want to say one more thing. Being D-Day today, I just want to say, we thank everybody. My father was on the beaches in Normandy 65 years ago today, so thanks, Dad. When I was a little girl, I used to wish upon the stars. They never seemed so very far away. Now that I am all grown up, I like to take my telescope. I love to go stargazing every day. If there were clear skies and I could see the stars, Jupiter and Mars, the sun so high it makes me wanna fly. I see the moon in June, but that little moon, let's go stargazing tonight. Take my hand and hold on tight. We'll wander through the magic of the splendor light. We see shooting stars, comets bright. Let's go stargazing tonight. Stargazing, you never know what you'll see. It'll be amazing, just you and me. Can't you see that Cassiopeia's not far away? Won't you come along with me and we can play? We'll put the sun to bed, we'll call it a day. Let's go stargazing tonight. Stargazing, you never know what you see. It'll be amazing, just you and me. Can't you see? So let's take a trip to the countryside. We'll see shooting stars and northern lights. We'll go to bed, we'll call it a night. Let's go stargazing tonight. We'll go stargazing tonight. We'll go stargazing
Thank you very much.
Thank you, that was wonderful, thank you. Just before we head out of the hall here, just to remind you, I have a number of displays members of the Ottawa Centre RASC have set up, talking about meteorites and telescopes and light pollution. So feel free to stop by and take a few pamphlets and magazines and all sorts of goodies there. We have, as far as I'm aware, when we entered this hall, there was still some sun out there. I'm assuming that sun is still with us, so we should have some telescopes set up. We say telescopes set up for solar observing. And but before we leave, just a few more things. One of the booths there, if there are people here who are interested in coming down to more of these kinds of events, again, throughout IYA and even afterwards, there's a sign-up sheet there if you want to leave your contact information, your name, email address, and we'll let you know of events that come up if you're interested in astronomy. Given that you're all here on a beautiful Saturday afternoon, I'm assuming you're all interested in astronomy, so again, we hope to see you at future events as well, and hopefully at some of our Ottawa Centre meetings too. And just a few people A few other people I want to thank who helped put this day together. Again, thank you to Carleton University for hosting us here, to the technicians, the crew here for keeping the sound and visuals going. Thank you very much for that. We've had a number of volunteers who put a lot of effort, just too many to completely name, but we've got gentleman, our videographer there, Eric Majala. Rob Dick was here a second ago. He was our photographer and also did a lot of the work really closely with the university to arrange for us to have this lecture here. Al Scott for his effort in helping to make Dr. Abraham's appearance here possible. And if there's one individual I think deserves a lot of appreciation, and that's our Ottawa Center's very own outreach coordinator, Mike Regatta. And actually, Mike, if you could come up here for a quick second. This is the part that Mike wasn't aware about, but just on behalf of the Ottawa Center RASC, and to all the people, yourself and all the people who put a lot of hard work in making this lecture work, thank you very much, and we appreciate that. And I think this is the point that concludes our lecture hall part of the day. So again, displays in the lobby, solar observing outside, and I believe Dr. Abraham will be here for a little while longer. If other people have questions they'd like to ask him, he'll be around. And so I'd like to thank you all for coming out, and we hope you see you all again at another event soon. Okay, thank you. Thanks, Matt.
Where the rocks split apart is where you get
Just enough to
ordinary rocks. A few parts of the rock that have vibration. Yeah, you can see the shadows.
It's not exactly centered here, but I normally don't use it anyway, but I like to use it. That's all it's all like an option.
Well, you know what I'll probably do? It's supposed to be
that's a good one. But, like, I don't know that
You can't see any detail, but you do see the red spot.